Yeah, you can, I think, start.
Hello everyone. Welcome to Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBC CPS IISc. It's my pleasure to introduce today's speaker, Professor Gugan Thoppe. He will be speaking on distributed network tomography, exact recovery with adversarial, heterogeneous, and sporadic data. Professor Gugan Thoppe has been an assistant professor in the Computer Science and Automation Department at IISc since 2019. He also serves as an associate researcher in the Robert Bosch Center, IIT Madras. He earned his PhD in 2016 from the Tata Institute of Fundamental Research in Mumbai. He also has postdoctoral research experience from the Technion Institute of Technology in Israel and Duke University in the USA. His research focuses on reinforcement learning, federated learning, stochastic approximation, and random topology. His research is supported by grants from CIFIPRA, Walmart, DST Serve, and NPCI. His work has been recognized with the Pradiksha Trust Young Investigator Award, the IISc Award for Excellence in Teaching, and the TIFR Award for the Best PhD Thesis. He is also an IEEE senior member and a member of the ACM India Eminent Speaker Panel. Over to you.
Thank you. So thank you everyone for coming to this talk. So as Shrishma said, and first of all, thanks to her and the CNI team for inviting me. So today I'll be speaking on distributed network tomography, exact recovery with adversarial, heterogeneous, and sporadic data. Okay, so here is the outline of my talk. Okay, so in the initial part of this talk, I'll introduce network tomography and I'll demonstrate that that can be represented or viewed as a distributed system of linear equations, and I will focus on the case where we only have access to possibly adversarial, heterogeneous, and sporadic measurements, right? And in this context, I'll talk about the limitations of existing adversary resilient approaches. Then I will introduce our novel L1 minimization based algorithm and discuss its convergence rates, and eventually I'll talk about or discuss some of the empirical results. Okay. All right. So here is a preview of what is going to come at the end, so that in case you decide to go out in between, at least there is this take home message, right? So we have a plot here. I will explain what this plot means and so on and so forth later on. But at this point in time, you can see that there is a dark blue curve in all of these 6 plots, right? And you can see that it starts slow, and in most of the scenarios, it actually goes beyond all the other curves, okay? And this is in some sense the essence of our work, that we are able to get more accurate estimates as compared to existing adversary resilient approaches. So that's the key take home message. So what this plot is and so on and so forth, we will sort of understand it as we go along. And I would also like to emphasize that the x-axis has a log scale, right? So it's not that for half the number of iterations our algorithm is slow. In fact, it's below or performing above other algorithms only for 1/100th of the iterations, whereas as we move along, one can see that our algorithm is able to get better and better estimates, and in the end one can see that the accuracy of our algorithm exceeds the accuracy or the the error that is present under other algorithms. All right. So with this picture in place, let me now begin with a quick description of network tomography. Okay, so let's say we have a network. So by a network I mean something like this that is shown over here. So a network typically we presume has some edge devices, let's say some personal computers, some laptop devices, some mobile phones, and so on and so forth, and they communicate with each other via a backbone network. Is that okay? And if you decide one day to become a network administrator, right, some of the goals that you would be asked to perform would include diagnose and fix issues pertaining to your network. In particular, you may be asked to isolate a problem source and thereafter allocate resources to address the problem. Okay, so in this talk we will focus on how to isolate a problem source, right? Like for example, the problem could be with high latency or packet loss and so on and so forth. So our goal would be to in some sense identify links. So you can see that there is a link over here with the solid black line, there is another link over here, another link over here. So our goal perhaps could be to identify links which have high latency or high packet loss rates. Okay, but the challenge in network tomography is that we cannot access samples related to link level information. Instead, what we have access to is end-to-end path level measurements. Okay, so for example, if we want to identify links with high latency, we would be in the problem of link delay tomography or delay tomography in short. Let's say there are a bunch of links, and on link k, let's say the delay is a random variable z of k, right, and a path is basically a collection of links, right, and the delay on path j, let's say we denote it by the random variable y of j, right, and if we have the additivity assumption, then one can show that the delay on path j is basically the sum of delays on the links that are present in path j, right, and since this is a linear sum, one can jointly represent y and z via this relation y equals pz, where P is what is known as the path link matrix. Basically it is made up of entries of the form AJK, where AJK is 1 if link K is present on path J, and so on, right. And in this talk, what we would be interested in is in estimating the expected value of this random variable Z given access to samples of the different coordinates of Y. Okay, so that is what we would be interested in. So here is a quick example. So we have a network here, there are 3 links, 1, 2 and 3, and there are 2 paths here. So the first path consists of link 1 and link 2, and the second path consists of link 1 and link 3. So one can see that the end-to-end delay on path 1 is Z1 plus Z2, and the end-to-end delay on path 2 is Z1 plus Z3, right. These two equations can be represented using the linear system of equations y equals pz, where p is this matrix. Okay, so one can see that because there is 1, 1, 0, if you multiply it with z, you will end up with z1 plus z2 here, and because there is a 0 here, you would end up with z1 plus z3, and that will be y2. Okay, so you can see that one can very easily construct a linear system of equations, and the key thing to note here is that this matrix P that you have typically would be a wide matrix, meaning the number of rows will be less than the number of columns. Okay, so that will add a level of complexity to solving this problem. Okay, and this is all about network tomography, and now I would like to tell you that we can pose it as a distributed learning or distributed estimation problem. So what do I mean by that? So let's say there are n workers, and the number of workers corresponds to the number of paths that we have. So let's say in this network that we have of interest, let's say there are n paths, and worker 1 is tasked to monitor path 1 activity, meaning it is basically going to take in measurements of end-to-end delay on path 1. Similarly, worker 2 is tasked with monitoring path 2 activity, and so on and so forth. Okay, so all these workers in some sense have access to, or I shouldn't say in some sense, so worker j has access to samples of y of j. Is this okay? So y of j is the jth coordinate of the vector y, and worker j we will presume has access to samples of y of j, and we have a parameter server. It takes in these estimates obtained by these n workers, and the job of the parameter server is to estimate some statistics of z, and in this talk we will focus on estimating the expected value of z. That's the goal. However, we will look at a slightly challenging case. The challenge would be on account of the fact that an unknown subset of these workers is adversarial in nature. Okay, unknown but fixed subset, right? So we don't know which subset of workers are adversarial, but they are fixed, and they will also be participating in this task. Okay, so they will also be sharing their estimates, and the parameter server wouldn't know. In general, we will presume that the parameter server is not able to detect whether the current estimate is adversarial or not, right? If it was very easy to detect, of course you can throw away those estimates, but we will presume that the adversaries are really smart, and they will adopt strategies so that it is not easy for the server to figure out if the estimate that is provided by this worker, whether it is adversarial or honest. Is this okay? So that's the setup we are in. So in this setup of distributed parameter server worker architecture where worker j has access to samples of y of j. Our goal is to find the expected value of z. That's the goal. Are there any questions? Yes. What do you mean by complete? So at this point, as I told you, this is some path in the network. Is this okay? Right. So for example, in this particular example, your worker 1 has access only to samples of z1 plus z2. Okay. Whereas in this case, worker 2 has access to samples of z1 plus z3. This is the setup. Okay. Now we will later see under what conditions we may be able to, perform this robust recovery, and under what conditions we may not be. So we will see that, but this is the current setup. Okay. And our goal is, given this setup, okay, and also presuming that some of the workers are adversarial, how can we estimate expected value of z? Okay, so one can quickly ask, okay, why would there be adversaries in a network tomography problem? Well, here are a bunch of high level reasons why they may be there. Okay, so a subset of workers may want to disrupt services that is being provided as part of this network, right? Or there may be a subset of workers, they may want to hide illicit activities, right? Like let's say somebody is downloading tons of data which they are not supposed to do, right? And they want to make sure that the network manager doesn't get to know it, in which case they may want to throw in measurements or pass measurements to the server so that the server is not able to know that they are doing this activity. On the other hand, the workers may also want to mislead traffic management. Okay, so one worker may want to have high bandwidth for themselves, right? So in which case they may want all other traffic to go via other sets of paths and links, right? And they may want to provide false data so that the traffic gets redirected. Or alternatively, the workers may provide false information because they want to sabotage competitors, right? Like let's say a part of the backbone network is controlled by, let's say, company A, and it doesn't like company B, right? And it may and company A may know that company B is performing very well and their network performance is outperforming theirs, in which case company A may want to provide false data so that the users may get the feeling that they are also performing quite well. So these are broad set of reasons for the presence of adversarial workers. Okay, so this is in some sense part 1 of the talk. We will now go to part 2 of the talk. Okay, so the goal is, in a distributed setup, when some of the workers are adversarial, right, how can we get hold of expected value of z? Okay, so one can look at existing literature and one can ask, how can we use existing literature to build adversary resilient approaches? So here is a quick survey so that you will know what has been done and in some sense the importance of what we are attempting to do. Alright, so here is a general formulation. For the time being we can keep network tomography at the back of our mind. Okay, so in a distributed setup, by distributed setup we mean that we have one parameter server and multiple workers, right? And some of these workers could possibly be adversarial, and let's say the joint goal of this setup is to minimize some function f of x, where f of x is the sum of these fj's, right? And we will presume that the joint goal is achieved perhaps by using some gradient descent type method or stochastic gradient descent type method, where the workers have access to noisy estimates of the different summands of this sum, right? And they can share these estimates with the server, and the server will use these estimates in some sense to minimize this function. Okay, that's broadly the goal of distributed optimization. For example, in the context of network tomography, this function fj, okay, could be the error on the jth coordinate. Okay, so pj transpose x is basically the jth row of your matrix P transpose x minus the jth coordinate of the expected value of the jth coordinate of y and the square of that, right? So recall that we want to solve y equals px type formula, right? So one of the ways in which you could go about solving is by posing this problem in this form, where the fj has some form like this. Okay, and then one can ask, perhaps we can directly use existing approaches and try solving this problem. Okay. So first let's understand, in a distributed parameter server setup, if there were no adversaries, how one would have gone about solving this problem. Okay. So this is the setup which I refer to as the naive approach, where there are no adversaries. Okay, and the naive approach is based on simple aggregation. So what do I mean by that? Okay, so we will presume that worker J has the capability to obtain a noisy estimate of the jth summand, that is, there is Fj, and worker J has the capability to obtain a noisy estimate of grad Fj at xn, and let's denote this gradient as Gn J. So J here denotes the worker index and N here denotes time. Is this okay? So each worker computes this estimate and shares it with the parameter server. So what the parameter server would do is, it will take all these estimates, do a simple average of these estimates, right, and call this as the aggregated gradient estimate, and use this in the gradient descent update rule. Okay, so xn plus 1, if your current estimate is xn, the server will obtain a new estimate by subtracting some step size times the gradient estimate. Okay, and notice that this gradient estimate is obtained by taking an average of the estimates that are shared by the different workers. Is this okay? And one can prove a result like this in a very straightforward fashion. I have taken a very recent reference, but one can derive these results using existing techniques which have been there for a long time. Okay, so let's say some assumptions like this hold, that is, your objective function f is strongly convex and each summand's gradient is Lipschitz continuous. So together this means that your objective function is strongly convex and smooth. So this is one of the easiest setups, right? And furthermore, as I told you, the worker J has access to stochastic estimates of the gradient of Fj, and we will presume that the expected value of this quantity, which in some sense quantifies the variance, this is upper bounded by sigma square times 1 plus norm x minus x star. So the idea here is that when x is very far away from x star, your gradient can grow, but when x is very close to x star, the variance is a constant. Okay, so that's roughly the idea here. And then if you choose this step size alpha n over here to be of the form c over n, where the c is a constant that needs to be chosen based on the convexity and Lipschitz continuity constants. So if you choose it appropriately, then one can show that this naive approach, okay, enjoys this convergence rate. Okay, and in particular you can see that you have a 1 over n convergence rate, and more importantly you have a capital N over here, where recall capital N corresponds to the number of workers. Is this okay? So one can see that if there were no adversaries, then doing this distributed optimization is actually beneficial, in the sense that you get a speed up that is proportional to n in this sense, right? More the number of workers, okay, the better the convergence rate would be in this sense. Okay, so indeed, if everything was nice, by that I mean there were no adversaries, and you use this simple aggregation idea, then this is the convergence rate that one would have enjoyed. Okay. Now comes the challenging part. Okay, what if some of these workers were adversarial in nature, right? So a natural question to ask is, could we have use this naive aggregation based approach? So what do you think should be the answer? Yes or no? If you use this naive averaging, what will happen? What do you think could happen? So these estimates, recall, come from workers. Is this okay? So if the parameter server blindly takes the sum, right, what could happen? Do you think something could go wrong? Like for example, if the adversary just puts in a large estimate, right, I hope you agree that the average can be very easily derailed. I hope you agree with me, right? So you can see that this naive averaging can be very easily derailed if some of the workers were adversarial. Okay, I hope this is easy to see. So one cannot use this naive approach when there are adversaries. So one can then ask, okay, what are the existing categories of approaches that have been attempted to do distributed optimization in the presence of adversaries. Okay. So my understanding of this landscape I have summarized over here. So broadly, the existing adversary resilient approaches can be grouped into three categories. Okay. The first is what is called as data encoding based approaches. The next is what is called as filtering based approaches, and there is a very exciting and recent category of approach that has come, I think, in the last 2-3 years. It is called as homogenization. Okay, so I will talk about each of these categories. Okay, the first is this category called as data encoding, right? So the idea here is to mimic what this naive approach did. Okay, but the way you do it is slightly different. So you can see some of these papers for this. Unfortunately, I didn't have space to put in the exact details, but our archive paper should have details of all these things, and if you want, you can ask me later. I'm happy to provide them. Okay, so in this data encoding based approach, worker J estimates some function of all these gradients. Okay, so notice that in that naive approach we had presumed that worker J only estimated grad Fj of x. Okay, here instead we will presume that worker J estimates some function of this, like for example, it could take some addition, okay, and with some linear combination, some other worker may take some different linear combination, and so on and so forth. Okay, and the idea behind these use of functions is that these functions should incorporate enough redundancy, okay, so that when these estimates of these functions are provided by the workers to the parameter server. So keep in mind that each worker is computing a different function of these gradients. Is this okay? Like the first worker could take the sum, the second worker could take the sum and difference of the first few quantities, and so on and so forth. I hope you get the idea, right? Xn here denotes the current estimate. Okay, so this is the gradient that we wish to compute, and each worker is tasked to compute some function of these gradients, and it shares them with the parameter server, and these functions have the property that these functions have to be chosen. So when I say function, I don't mean f, okay, I don't mean f or f1, I mean some there is a function that combines them in a careful way. That is the function that I'm talking about, and this function should have the property that it has enough redundancy so that by using these different estimates, the parameter server is able to reliably reconstruct grad f of xn. Now one can see the motivation, right? If the parameter server had access to grad f xn, right, which is basically the average of these different quantities, right? So grad fx would be the average of these quantities. So if the parameter server somehow managed to get hold of this, then it can run the usual gradient descent, no problem, right? However, the problem with this approach that is based on data encoding is that if you look at it from the perspective of network tomography, then each worker would be forced to process samples of multiple y coordinates. Okay, so if you recall this f function that I had suggested, okay, so notice that worker j over here is presumed to have access only to samples of y of j. Is this okay? So y of j is the end-to-end measurement on path j. So if you want to compute the gradient of this and the gradient of this function for different j and take some combination of them, that would imply that worker j has access to samples of multiple y coordinates, and in general this is not feasible in the context of network tomography, right? And also in order to be able to reconstruct this grad fxn, one would need that all workers share their estimates of these functions of these gradients synchronously with the server, so that the server can take in these estimates and reconstruct grad fxn. Okay, so this is the issue. Okay, so this is a quick summary of data encoding based approach. Now let's move on to the other category of approaches, which I refer to as filtering based approaches. Now filtering based approaches can be further subdivided into synchronous approaches and asynchronous approaches. By synchronous I mean the parameter server expects all workers to provide their estimates more or less at the same time, and an asynchronous I mean perhaps only a subset of the workers provide their estimates, right? And that's the view I will be taking. So the synchronous approaches in particular include the ideas which are based on the use of robust aggregator. So an example of robust aggregator is median, trimmed mean, geometric median, and so on and so forth. I'll talk about them soon, right? So this is the idea of using robust aggregator. So compare this with the simple average that we did. So the simple average is not a robust aggregator, because even if one worker shares an adversarial estimate, the average can be derailed very easily. However, derailing the median and trimmed mean, which are examples of robust aggregators, are not that easy. Is this okay? Trimmed mean means that you take in some estimates, throw away the outliers, and take the average of the remaining guys. Okay, that's what trimmed mean means. Trim means you trim the data list and then take the average. Okay, so something as simple as that. Okay, so among the asynchronous approaches, so by asynchronous, again recall what do I mean. I presume that the parameter server at any given time has access only to samples of estimates by a subset of the workers. So not all workers have managed to share their estimates. So in this case, how does one go about handling adversarial measurements? So one class of ideas is based on the use of private data at the server level. Then there is some idea that is proposed by Damaskinos in 2018. Okay, this is based on the idea of what they refer to as the Lipschitz filter, right? And then there is also this idea from 2021 by Yang and Lee, which talks about keeping this asynchronicity only at the server side. Is this I should say, okay, there is a typo here. This should be synchronous server side updates. Okay, sorry. So the workers are asynchronous, but the server is synchronous. By that I mean the server waits before doing the gradient estimate until it has estimates from enough workers. Is this okay? So that's roughly the idea of synchronous server side updates, right? So now I'll tell you broadly why these approaches are not suitable for network tomography, or what are their limitations. Okay, so let's begin with this synchronous idea. Okay, so synchronous idea which is based on robust aggregation. Okay, so unlike the data encoding scheme, here we will presume that worker J, okay, is only responsible for sharing an estimate of grad Fj. Okay, so this is in line with what we want in network tomography, right? And we will presume that this is a synchronous setup. By that I mean all workers are supposed to share their estimates more or less at the same time with the server, and the server does some aggregation of these estimates. So if you have this gn1 to gnn, so capital N is the number of workers and n is the time instance. So if the workers send these estimates, the server does a robust aggregation of this. So examples of such aggregation include coordinate wise median, coordinate wise trimmed mean, geometric median, and so on and so forth. Okay, okay, and sorry about that. Okay, so that's what do I mean by robust aggregator. Okay, so the issue with robust aggregator is that if your gradient estimates have some heterogeneity. Okay, what do I mean by heterogeneity? Suppose the expected value of this quantity, right, is some constant. Okay, like for example, this is the gradient of the jth summand, and this is the average of all the gradients. So if there is some gap between them, we will say that there is some heterogeneity in your measurements. Is this okay? So the gradient estimates that are available to worker J are different from the gradient estimates that are available to worker I. Is this okay? So this is what do I mean by this heterogeneous case. So if you make use of this robust aggregator in the presence of heterogeneity, okay, then what one can guarantee is that the gradient descent, where the gradient estimate is computed using some robust aggregator, okay, that can only converge to a approximate solution. In particular, the radius of the ball to which it can converge to can be shown to be proportional to zeta square, where zeta square in some sense captures the heterogeneity gap. Okay, so more diverse or more different the gradient estimates are, the larger the size of the ball to which your your gradient descent algorithm is guaranteed to converge to. Does this make sense? Okay, so here one cannot have exact recovery in the presence of adversaries. In particular, this is the case where the gradient estimates are heterogeneous and adversarial, which forces you to make use of these robust aggregators, and you can only guarantee convergence to a fixed size ball where the size of the ball in some sense is proportional to the heterogeneity gap. I hope this is clear. Okay. So this is the issue with this robust aggregator. In fact, one can show that this is also the issue with the use of Lipschitz filter, and also the same issue persists with synchronous server side updates. Okay. So before I sort of give you a overview of what these approaches do, let me give you briefly what is the idea of private data. So the idea of private data here is that the parameter server is presumed to have some exclusive access to honest data, right, real data which is uncorrupted by adversaries, right, and then whenever a worker shares a gradient estimate, what the server will do is it has access to some local data, it will try to compute the gradient using that local data, and whatever the gradient estimate has been shared by the worker, it will compare that gradient estimate with the local gradient estimate. So if they are having good correlation, then the worker will say, okay, this is a honest gradient estimate. However, if there is too much divergence, it will say that, okay, I'm going to reject this gradient estimate. Okay, so that's the idea of this private data based approach. However, in this again is not very suitable for network tomography, because this would correspond to the server having access to true measurements of different paths, right, and network tomography in a sense becomes useful only when there is some drastic change in network performance, right, like you during routine operation behavior, okay, network tomography is as such not useful, but as soon as the routine behavior changes to abnormal behavior, that's when network tomography will become useful. So at that point in time, presuming that the server has access to the true path level measurements is a bit infeasible, and that's why this private data based approach is not very useful. Okay, in the interest of time, I'll skip this Lipschitz filter based approach, but here again the issue is this. Okay, so now I'll focus on the asynchronous worker side updates. Okay, so the idea over here is as follows. So what the server does is it creates many buckets. Okay, and what is the idea of a bucket? It will put some of these workers in each of these buckets, like bucket 1 could have worker 1, worker 2, bucket 2 could have worker 3 and worker 7, and so on and so forth. Okay, so it forms buckets of these workers, and then what the server does is it waits until at least one worker in each bucket has provided an estimate. Okay, so we are in the asynchronous setting now, right. So in the asynchronous setting, if there are too many workers and if the server waits until every worker provides their estimates, okay, so the server has to wait for a very long time until it does a update of its solution estimate, right. So the alternative is to ensure that again there is a typo here, I should say synchronous server side updates. The idea is to form B buckets of workers and ensure or wait until only at least one worker in each bucket has provided an estimate. Okay, and some buckets will have more number of estimates, some bucket will have one. In any of these cases, the idea is to take an average of all the received estimates in bucket J to come up with an average H and J. So n here corresponds to time and J here corresponds to the index of the bucket. Is this okay? And then what the server does is it takes a robust aggregation of only the outputs of the B buckets, right. So earlier the idea was take a robust aggregation of outputs of all the n workers. Here we are saying that since the workers are behaving asynchronously, I will only wait until a worker in each bucket has provided an estimate, and then take these estimates and take a robust aggregation and then perform a gradient descent type update. Okay, so this is what is the idea in asynchronous, and as I mentioned, again the issue with asynchronous is that one can only guarantee convergence to a fixed size ball, and the size of the ball depends on the heterogeneity gap. Alright, so there is a recent work, I think I forgot to put the reference here, by Sai, Karimi Reddy and group, okay, from 2022, okay, and they introduced this homogenization approach. Okay, so let me first give a motivation for why one may want to talk about homogenization. As I told you, the use of this robust aggregator in presence of heterogeneity gap, okay, only guarantees convergence to a fixed size ball. That is the issue. So what Karimi Reddy and that work talks about is there some way we can homogenize the estimates? If we could homogenize the estimates and then take a robust aggregation, then things will work fine. That's the idea. So the way they achieve it is the following. So again, this trick works when the workers are synchronous. So what the idea is, you first randomly permute workers. Okay, so you have worker 1 to worker n, you randomly permute them. After you permute them, you put them in different buckets, right? So in each run, if you have bucket 1, the number of workers that are assigned to that bucket will be different. Okay, that's the idea of, you know, random permutation and then assigning the buckets. Okay, and then you know, you do as you did in the asynchronous case, that is, you know, you take the average of all the estimates in bucket J to output this, and then the server computes this robust aggregation. But the key difference between this and the asynchronous case is that in the asynchronous case, the server waits as long as, or server waits until there is one estimate in each bucket. Okay, whereas in this homogenization trick, you know, the server waits until all the estimates are provided, and of course this will, you know, be useful only when the workers are more or less synchronous, right? And but the idea is very similar to the previous one, except this random permutation. Okay, so now because the workers are randomly getting permuted, the you know, the distribution of each of these quantities will now more or less be the same. Is this okay? Because they are same, in a sense you can understand that they have been homogenized, and because they are homogenized and thereafter the robust aggregation is being taken, right? So here the heterogeneity gap as such wouldn't affect the you know, the performance of the algorithm, and they have indeed proved a result of this form. They have said that suppose there is a constant k which is of the order 1 over delta, where delta is the fraction of adversaries, and if your you know, the difference between the gradient of the jth term and the total gradient, if this satisfies a condition like this where k is you know, is of the order 1 over delta, then one can actually guarantee exact recovery. Is this okay? So let me just summarize. Heterogeneous workers, synchronous workers, some of these workers are adversary. If you do this homogenization trick, then under some broad set of conditions, one can actually guarantee exact recovery. Is this okay? So this is the setup, but you know, because of this condition, okay, our interpretation is that, okay, here one would require that the I mean, you can rearrange this term and one can ask, you know, for a fixed case k value, what should be the value of delta, and one can see that here one would require that the delta be less than 1 over k square. Okay, so in which case we would require that delta be sufficiently small. In other words, the fraction of adversaries, when it is sufficiently small, okay, only then we can guarantee exact recovery in this case. All right, so this is an overview of existing approaches, right? And with this in mind, we will now talk about our approach, okay, which is you know, takes a very different approach to what we have discussed so far. Okay, so before I talk about our approach, let me give a quick idea of how we come up with this, how we came up with this approach. Yes. Yeah, so as I told you, whatever I discussed is for a general case, right? And we will eventually relate f and p in this fashion. Now I say in this fashion because this fashion will not work, but we will see something similar to this that we will be using. Okay. No, we will presume p is known. So the path link matrix is known, but which workers are adversarial, that is not known. So the estimates that the workers provide, that could be potentially adversarial. Okay, so now we are going to propose a new approach to deal with this network tomography estimation problem in the presence of adversaries. And in order to motivate our approach, I will begin with a very basic problem. Let's say there is a vector x star, and let's say there is a matrix A. You know this matrix A, you don't know x star, but what you have been given access to is the value of B. Okay, so you know A, you know B, and then one would like to ask, if I know A and I know B, how to recover x star? Well, this is the very basic case of solving a linear system of equations. You know A and B, there are multiple algorithms, and one can show that, you know, because B is in the column space of A, if A has full column rank, one can exactly recover x star. Okay, very good. So now let's slightly complicate this setup. Okay, so let's say we again are in the case where there is a x star and B is A x star. So you know A, but this time you are not told B. Okay, instead what you are told is B prime, which is a corrupted version of B, and the corruption is given in the following way, that B prime is B plus E. So you don't know B, you don't know E, but you know that E is M sparse, that is at most M many coordinates of E are sparse, and you have been given access to B prime. Okay, so now the question is, you know A, you know B prime, can you recover X star? Okay, so this idea was looked at in this paper by Fauzi, Taboda and Digavi, right, and they said that, you know, in this case one can actually you know, look at this L1 minimization problem. So notice that you use this A and you use this B prime, you don't know B but you only know B prime, so you use this B prime and solve this L1 minimization problem, and they said that you know, by solving this you can recover X star if and only if. Okay, so notice that if you use L1 minimization to recover X star, then you can recover X star if and only if A satisfies some robustness condition which is defined over here. So let me just take you through this condition. Okay, so this condition says that you know, AI transpose X for I in S complement. So this quantity should be greater than AI transpose X for I in S, and we require this condition to hold for every S whose cardinality is less than M, and we also require that this condition hold for every X. Okay, so we require that this condition hold for every X and every S subset of 1 to N whose cardinality is less than M, where M is basically the sparsity of the error vector that has been introduced. Is this okay? So we require some strong condition on this A matrix, and that condition is over here. So the basic interpretation of this idea is that if you interpret this as some energy, then you know, on a few set of coordinates, because the cardinality of S is small, so on a few set of coordinates you shouldn't have too much energy. Okay, so that's rough, I know, a very hand wavy interpretation of this condition. So if you have this condition and you solve this problem, you will actually be able to recover this X star uniquely. Okay, so what we have done is that, can we, I mean, we asked ourselves, can we extend this idea to our setup, to the network tomography problem? That is the thing that we have, you know, asked ourselves, and one can immediately check that, you know, some of the examples of A matrix which satisfy this robustness condition include, you know, these. For example, this matrix can handle 2 adversaries. Okay, this matrix on the other hand handles 1 adversary, right, and you know, this matrix and this matrix indeed satisfy these conditions for M equals 2 and M equals 1 respectively. Is this okay? Now it's not difficult to see that, you know, this condition will actually be satisfied only when A is a tall matrix. Okay, so that is the first problem. If you now connect it back to the network tomography problem, your P matrix was wide. Okay, now on the other hand, this idea over here requires that A be a tall matrix. So the first question we asked was, how can we connect P and an A matrix of this form? Okay, so this is what we did. Okay, so suppose there are matrices A and B such that your expected value of Z satisfies this condition. Okay, so P is a wide matrix, but suppose it has a decomposition such that at expected value of X this relationship holds. Okay, so I am being very careful. I am not saying that P is AB, I am saying that for expected value of Z, P and AB satisfies this condition. So P is a wide matrix, but A is a tall matrix which satisfies the condition that I mentioned previously, and B is some wide matrix. Okay, so if you find A and B such that P times expected value of Z equals A times B times expected value of Z, then what we claim is that if you now solve this problem, okay, we are not guaranteeing that you will recover expected value of Z. Instead, what we are saying is you will be able to recover B times expected value of X robustly. Is this okay? I hope this is clear. So let me just summarize. You have access to P, which is a wide matrix in network tomography. We cannot directly apply this idea, okay, to that setup because our P matrix is a wide matrix. So what we are saying is, suppose you find some decomposition of P such that such a relationship is satisfied for expected value of z, then one can solve this problem and recover robustly b times expected value of z. Okay, so we give up on recovering expected value of z, but we say that b times expected value of z you can robustly recover. Okay, so that's what we try to do, and this is basically our proposed algorithm. Okay, now before I go over the algorithm, I would like to draw your attention to the title of this talk. Okay, it said exact recovery with adversarial, asynchronous and sporadic data. Okay, so now I'll connect those three words to this algorithm. Okay, so what we will presume is that at any time n, only one worker, okay, we are in the asynchronous setting, we will presume that only one worker sends in its estimate. Is this okay? And that estimate is basically this little yn, and this little yn is basically an average of the capital Y's it is measuring. Okay, so capital Y is basically the sample of the end-to-end path measurements. Okay, and each worker will keep doing this averaging of the different measurements it gets, so that it has a better and better estimate of expected value of y for the path that it is monitoring, and it will pass on this information. Okay, so note that whichever worker in plus 1 is sampled at time n, okay, that worker will send in this information. So notice that this is some sign of some expression. Is this okay? So the key thing to note here is that worker I, whichever is selected at time n, only is required to send a sign of some expression, which means it is only required to send plus 1 or minus 1. Okay, so how is this worker chosen? We presume that the server chooses this worker uniformly randomly, but this is not important. What is important is, or this is not restrictive, we can modify this algorithm to the case where each worker is chosen with some positive probability. Okay, we shouldn't be in a case where honest workers are never chosen and only adversarial workers are chosen. That would be the case where some honest workers are chosen with 0 probability. So that is the case we want to avoid. As long as every worker is chosen with positive probability, this algorithm will work. Okay, so what is the idea? At time n, the server will first sample the index of the worker, okay, and send your current solution estimate to that worker. That worker will quickly obtain a sample of that path level measurement, do a running average. So this little yn is basically a running average of these capital Y's, and send that value in the form of this sign expression to the server, and the server then does this update rule. Okay, so what is important here is at time n, notice that there is an estimate only from one worker. Okay, only from one worker, but whereas if you recall the aggregation based ideas, you needed estimates from all the workers, and then you did some median and trimmed mean and such and other ideas. Whereas we can work with one estimate and you directly add it to the xn, and then there is some projection operation. Okay, the projection is done onto some calligraphic set x, which is known to contain your true solution, that is b times expected value of z, and this x, as long as it is compact, it is good enough. Okay, we require that it be compact. We are not saying that it has to be small or anything, but we require that it be a compact set, and this is the update rule. Okay, so notice that at any given time it suffices if only one worker shares their estimate, right? And here, what is this quantity? One can show that this is basically the gradient of this expression, where this b prime is now replaced by expected value of y. Is this okay? So what we are doing is basically the stochastic gradient descent of this objective function, where b prime is now replaced by expected value of y. That is exactly this expression that we would obtain, and then there is this sine function. Okay, so let's understand what is the role of this sine function. Now if a worker is adversarial, what is the worst they can do? Okay, because the impact of adversary is contained only in this sine function, and we presume that this A matrix is known. Okay, so the adversarial worker cannot destroy this value in any way. So the only thing that the adversarial worker can do damage to is this quantity. So what is the worst it can do? If the sign is actually -1, it can flip it. On the other hand, if the true sign is +1, it can flip it. So in other words, because of the presence of sign, which comes because we are doing a gradient descent with respect to an L1 minimization problem, the worst that the adversary can do is flip the sign. Okay, so that is the key thing to keep in mind. So in some sense, whatever the adversarial worker does at the level of server, it only sees a flip of sign. Okay, so that is the key thing. And now I'll talk about our main result. Okay, so our main result is that under some assumptions, and if you choose some step sizes of this form, in particular notice that for the update rule at the server, we work with a step size of the form 1 over square root n plus 1. And if you recall that naive approach, there the server was working with step sizes of the form 1 over n. Okay, here instead we work with 1 over square root n, and one can show that if your gx is this function, and if you look at the error with respect to this function for some tail average of your estimate. So xj is the estimate given as output by our algorithm at time j. You look at some tail averaging of these estimates and look at the error at this tail averaged estimate, then one can show that this error decays at 1 over square root n. Is this okay? So that is the summary of our main result, and in the interest of time perhaps I'll skip the proof idea and now directly jump to simulations. Is this okay? So what do we want to do? On one hand, we have these bunch of approaches that are there in the literature, which is based on synchronous workers, asynchronous workers, use of robust aggregation and so on and so forth. So there are a bunch of ideas, and we want to compare those ideas with our algorithm. Okay, that's the idea. So we consider a very simple network which is given in the following form. Okay, so we have around 5 edge devices, 3 backbone network devices, and there are a bunch of links. Okay, and here is the path link matrix corresponding to this network. For example, if you try to read this path, it has 1, 1, 1 here. So this is link 3, link 4 and link 8. Okay, so link 3, link 4 and link 8. So basically it represents this path. Okay, so in this way, every row of this path link matrix corresponds to some path in this network. And the key thing to note here is that you have 8 columns and 7 rows. So which means it's a wide matrix, and we are working with 7 paths in the networks, and there are 8 links over here. You can see that L1 to L8. So that's why we have a matrix of size 7 cross 8. Okay, so we say that if some of these measurements are adversarial, okay, we won't be able to do much. So what we do is we try to find a decomposition. As I told you, we want to find a AB decomposition such that P times expected value of Z equals AB times expected value of Z. So here is a matrix for that decomposition. So we have identified some conditions under which this decomposition holds, and you can see that this is a tall matrix, okay, and it has 7 rows and 4 columns. And one can show, we have shown that this matrix over here satisfies that robustness condition which we saw from that Digavi et al. Paper, right? And this matrix can handle one adversary. Okay, so if any of these measurements are adversarial, it is fine. We will be able to do exact recovery even if there is one measurement that is adversarial. Okay, and this A matrix comes from this P matrix. Okay, and then we do a comparison of our algorithm with existing approaches. Is this okay? So I would now tell you what we do in each of these plots. Okay, so what we have done is we do L1 minimization, and I hope you agree that L1 minimization is a non-smooth optimization. Is this okay? So non-smooth optimization in general is known to have smaller convergence rates, right? So what we did was we used L2 minimization for the other approaches. So L2 minimization because that's a smooth, strongly convex objective function. So what we did was, except for our approach, we used a L2 minimization for all these problems. Is this okay? And now the jth function, so maybe I'll just write it over here. Okay, so we have this A times X equals expected value of Y, where this A is basically this tall matrix. Okay, and we want to solve this problem. So for our setup, we look at the L1 minimization, and for the other approaches, what we did was we looked at L2 minimization. Is this okay? This is what we did because this is strongly convex, this is non-strongly convex, and we wanted to see if we can use these the other ideas with this objective and how does it compare with this. and here one can see that fj of x will be aj transpose x minus expected value of y of j the whole square. Okay, so this is what your, it can be open. I'm not sure if you can see this. Can you see this? Okay, so this is what the jth function is, and we will presume that whatever idea we have over here, okay, that makes use of this. So let me just take you through the different approaches. So these are the different aggregators that are being used. So we have something called as CTM, which stands for coordinate wise trimmed mean. Then we have coordinate wise trimmed median. Then there is some aggregator called as CRUM. Then there is some aggregator called as RAGE. These are different popular aggregators. And then there is RFA, which is basically a geometric median. Okay, so these are the bunch of ideas. So here we basically make use of, you know, synchronous approaches. Okay, so the top row corresponds to the case where all workers share their estimates with the server at the same time, whereas the bottom row corresponds to the case where the only one worker shares their estimates with the server at any given time. So this is the asynchronous scenario, this is the synchronous scenario, right? And if you see, we also make use of 5 other algorithms here. This is the variant of this algorithm that uses bucketing. If you remember, I said there is this idea of homogenization. Okay, so these are the variants of these approaches where bucketing is used. Okay, and then we compare these 10 algorithms with ours, and the difference between this and this is that in this case, since we are working with strongly convex setting, we presume that for the server's update rule, if we made use of a step size like 1 over n, that would actually be good, right? And we compared it over here, and one can see that if you zoom in over here, our algorithm is able to go below all the other algorithms. Okay, so then we said, okay, maybe 1 over n is not the good step size, so we now used 1 over square root n for all the other algorithms. Okay, and then we saw that many algorithms become, we go below many algorithms, but there are still some algorithms which closely compete with ours. So then what we did was we multiplied the A matrix by 10, okay, artificially. So why did we do that? By multiplying the A matrix by 10, we are increasing the heterogeneity. Okay, so if you look at this function, if you look at the gradient of this, if your AJs are multiplied by 10, you would have higher heterogeneity. Now in this case, one can see that once there is enough heterogeneity, again we see a behavior which is very similar to ours. Is this okay? So in other words, when there is heterogeneity in the gradient estimates, right, then our algorithm seems to be performing better than other algorithms in the presence of heterogeneity. Okay, so that is the idea over here, and this is the same story with asynchronous workers. Here again one can see that in all these cases our algorithm is able to provide better accuracy. Okay, so now let me conclude. Okay, so a summary of what we did was we discussed a novel L1 minimization approach for exact recovery with adversarial, asynchronous and heterogeneous data. We discussed a convergence rate of 1 over square root n, okay, which is optimal for non-strongly convex optimization, right, but it is not good compared to strongly convex optimization. Okay, so that's the reason we compared other approaches where we actually work with strongly convex optimization. Okay, and we saw that our algorithm is even able to show better accuracy compared to these homogenization based tricks. Okay, but at the cost of having the ability to find such an A matrix. Okay, so how do you find an A matrix is something that we have manually done over here, like we had to use brute force techniques to come up with this A matrix. We are saying once you find this A matrix, our approach is going to perform very well, whereas the other approaches as such don't need this knowledge of A, right? And then we showed empirically that our algorithm has higher accuracy, especially when there is higher heterogeneity gap, right? And in future directions, one of the goals that we wish to pursue is how to automate finding this A matrix. Right now, as I told you in that application, that A matrix was hand designed. Okay, so that is of course not feasible in practice. So we will have to figure out a way, and we believe some ideas from compressed sensing would be useful here. Okay, and then we wish to extend our ideas to the problem of tracking. So right now here we presume that the mean delay across every link is fixed. Now imagine a scenario where it changes with time. How would you go about tracking the change thing? in the presence of adversaries. Okay, so that is the idea. And the last idea that we wish to pursue is, can we extend this idea to general optimization? Right now we are only in the case of solving a linear system of equations, but we wanted to extend these ideas to general optimization. What would be the right way to go about doing it? Okay, with this I'll stop. Thank you. I'm open to questions. Yes. Sure. Yeah, so we don't presume, we don't make any assumption about adversaries. So the adversaries can do anything, but notice that our algorithm bounds the effect of adversaries by making use of this sign function. Is this okay? That is the key thing. So even though the adversary can do anything, the impact on our algorithm is bounded because we are making use of this sign function. Okay. Here there are some cases where the rows can be, I don't know what do you mean by homogeneity. Is this okay? So homogeneity in a sense means that some expression like this should be bounded. Okay, so if you this is the heterogeneity gap, which so fj is the gradient of the jth term in the sum, and f is basically the sum of all the functions, the average of the sum of all the functions, and then you take the gradient. Is this okay? And the expectation here is when j is chosen randomly, how does this gap differ? Is this okay? This is the definition of heterogeneity. Okay. Yes. On what? On the sign, yes. So here, I would answer your question by going back to this paper, because this paper looks a simpler variant of our problem. Maybe I'll just tell you how is this simple. Here we presume there is a one-time attack. Okay, so instead of getting B, we get B prime, and we can take this B prime and A, go home and solve this problem. Okay, and when you are at home and solving that problem, none of our intermediate estimates are attacked by the adversary. Whereas in our case, we presume that each time we make a measurement, right, the adversary can actually impact our estimate. So this is like frequent attacks in our case, whereas there is only one time attack. Nevertheless, the answer to your question is, so your question was what is the sufficiency conditions, right? So if you go to this paper, they say that as I told you, there is this sparsity idea, and they exploit this sparsity idea to ask what is the necessary and sufficient condition that given B prime you can recover X star. So they first look at the problem from the L0 minimization problem. Okay, and then they provide some sufficient condition. Okay, and if I'll have to recall to the exact thing, but you can read that paper. And what they say is that instead of L0, if you use L1 minimization, okay, then this is a necessary and sufficient condition. That is, if this condition holds, you can recover X star exactly, and if this condition doesn't hold, then you can find an X star for which you won't be able to recover. So with L1 minimization, this is a necessary and sufficient condition, but if you for some reason manage to go beyond L1 and closer to L0, I don't know how to do that, but if you could do that, then one can weaken this condition a bit, because the condition for exact recovery with L0 minimization is weaker condition than this. Is this okay? I hope that helps.
Thank you, Professor, for the very informative talk. Thank you, everyone, for attending. And we have arranged refreshments in the coffee hut. Please have them and continue conversations there.